Let's dig a little deeper now in our understanding of stresses and how they affect the material that we make our parts and components of. Let's have a quick review of what we've thought about and discovered so far. If we have a simple member that has direct tension in it, what does that mean? Well, we just have two forces. This is a two-force member. The load acts along the centroidal axis. Simple, let's say it's a rectangular beam, so there's the cross section. If we were to cut the beam and look at it, this is what we would see. We could, calculate area properties, moments of inertia, where the centroid's at, all those sorts of things. And as long as we cut the beam somewhere in the middle, we assume that the force that's being applied would essentially be spread out across the entire face equally, and then we could call it stress. And the stress would simply be equal to the force over the area. So however much force there is divided by the cross-sectional area, that's the level of stress, assuming that the stress is distributed uniformly over the cut area. So what if we consider an isolated stress element? So we're going to start drawing a lot of little bitty blocks, and what we're doing is we're thinking about what's going on in that little bitty block. How is that block remaining in equilibrium? Why doesn't that block just rip out from the material? So you see the small isolated stress element, just a little black box. If we expand it and look at it, so we're just looking at it from the same perspective here, then the stress on the right hand face would be equal to simply F over A. But for this element to stay in the material and not move around, there must be a similar stress on the opposite side. Now your intuition may be asking for a shear stress. There's a reason there's no shear stress in this case. If you're thinking, well, I see that I need to balance the load on either side, right and left essentially, but why couldn't I just put a shear on the top of this thing? Well, if you put a shear on the top, now you've got a moment, right, and it can rotate. And to prevent that from happening, you'd have to put an opposite shear on the bottom face and then two more shears on the left and right face. And it turns out that would not work because you could never generate a left and right net load or force or stress with shear stress. So we have to have normal stress on the left hand face, which is buried in the material, just like you see in that black box. It's deeper into the material from the cut face, but still there has to be stress at that point. And it makes sense, right? I mean, if you imagine cutting to the left of this box in the beam, cutting the whole beam, you'd have the same area and you'd expect the same stress distribution on the left hand face. So all of this should make some sense. Of course, the magnitude of the normal stress then is force per area, so it's pretty easy to calculate and use. For compression, the only real difference is that the forces are inward instead of outward. Instead of pulling it apart, trying to compress it together. Same area, we consider that same stress element, and now the direction of the stress is just into the material, trying to squish the material instead of trying to pull it apart. In that case, we designate this, it's still a normal stress of course, but we just designate it with a negative sign to indicate compression. So again, we're assuming uniform stress across the entire area. Again, the only difference being that now we've got a negative sign for our stress instead of a positive sign, indicating compressive stress instead of tensile stress. Now what about for bending? Well, we've studied beams, and we know that if we set up a beam with 4-point loading like this, where the magnitude of the load and the reactions is simply F, we can write or compute a shear diagram and a moment diagram. The shear diagram is pretty simple because the reaction on the left is magnitude F, the load at position B is magnitude F, and so of course your shear diagram would go up to a magnitude of F, go over, and then drop down to 0. So the point of all this is that in the center of this beam there is no shear. Now there is a moment, because if you look at the integral of the shear you get the moment diagram. And so if you add up area as you're moving from 0 to point B across distance A, the magnitude of the moment is just the area of that rectangle, so it's just F multiplied by A. So the moment, once we get to point B, is F times A, and there's nothing to change it, right? There's no area in the shear diagram to integrate in order to affect and change the moment. So the moment in that center section between B and C is constant. There's no shear, there's only a moment. And so if we were to extract some of that section of the beam, it wouldn't really matter exactly where we cut it, right? I mean, we could cut it at E, for example, and then over to the right a little bit. Then we could imagine this section of beam that has a pure moment applied to it. And you can see the the moment applied to either side of this beam. That's really what the moment diagram is telling us. Now, if we consider this section of beam, you probably remember from our study on bending of beams that the stress distribution ends up being a compressive stress in this case at the top, a tensile stress at the bottom, and linearly changing from one to the other across the width, or the height of the beam. And so we can calculate all these things, right? I mean, if we have a stress element Q and a stress element R, we can calculate the stress at Q. It is a normal stress, so it's just my over I, where y is the height of Q. If we're considering the stress at R, it would be my prime over I. Of course, at the top, at Q, that whole upper half above the neutral axis is all compressive, so we get a negative sign, and down below the neutral axis we'd always have a positive sign on the stress indicating tension. And of course the stress is the maximum at the upper and lower portions of the beam, the upper and lower surface, and so if we're interested in the stress there, then we'd use MC over I, where all we're really doing is substituting C, the maximum distance from the neutral axis to the outer fiber, for I. So it's just a special distance because it's from the neutral axis all the way out to the extremity of the beam's height. Now, if we were to extract the stress element Q and look at it, we could draw the stress on either side. Being a normal stress again, it would just be my over I. Since this is Q, that would be negative my over I, and we can certainly calculate the magnitude of those stresses. And similarly at R, at the lower half, it would be tensile stress, and it would be my prime over I, as I said. I think I got ahead of myself a little bit in the slides, but you get the idea, right? We've seen this. This is nothing all that new. A lot of times we realize that what we're really interested in is the maximum stresses, and so we make the substitution of C over I for 1 over S, or essentially the section modulus. And the whole point of this is that, if what we care about is the maximum stress, we don't really need to bother with, some height. We're just interested in C, which is the maximum height away from the neutral axis. And of course, the cross-sectional property, the second moment of area, does not change, so I does not change. And it's a little bit more convenient form for calculating the maximum stresses in the material. And a lot of times what we really care about are the maximum stresses. So it's really important to begin to remember these stress distributions we've discovered, because you really want to know where the stress is maximum, because that's where problems are going to occur in the material. I guess it would be fair to say you're interested in areas where there's no stress, because essentially those are areas you can usually remove material from and have essentially just as strong a part or beam or whatever the case may be. Now, we also considered direct shear. And if we think of a workpiece here being clamped between two jaws and a shearing cutter that's coming down to shear the workpiece, there's a shear plane you can see, and it would have some area AS. If we extract just the workpiece that's between the clamps and imagine it's already sheared off or is being sheared off, well, then we could look at it and realize that this surface has all shear stress on it, right? I mean, it's pretty simple. It's a downward force that lies along the cut plane we've imagined here, and so it must be a shear stress. And it's just the amount of force being applied by the shearing cutter divided by the shear area. So you can see the shear plane and so forth. Now, I've extracted an element here, but it's different than what I've done so far, because you might think that we're, with this element we're looking at the shear face. We're not. That's not the case. Be very careful here. The right-hand side of this shear element represents the entire black box that you see on the shear face. It's just the right-hand side. Really, this is a cube, okay? Imagine it kind of like a Rubik's Cube, okay? It's got 6 sides, or, it's just a square box. And so on the right-hand face, that's where that downward shear is located. You can see that the direction matches on the right-hand face. But within the material, back in the area where this material is clamped, okay, go back in the material a little bit, that's the left-hand face. And then the upper face, where we've got shear going, I guess it'd be backwards for the video, so it'd be going, right to left for you. That shear is a byproduct of the shear on the front face, right? That front face that we see exposed has shear pointing downward. We have to have shear pointing upward on the left-hand face in order to keep this cube from accelerating upward or downward, right? Well, but that causes a force couple, essentially, or I guess you could say a shear couple, that has to be counteracted by the upper and lower shears that counteract, of course, each other to prevent motion left and right, or acceleration left and right, and to also counter the tendency of the vertical shear stresses from rotating the element. So all of this really is just statics. That's really all it is statics on steroids, I guess you could say, where we're considering shears, and technically the stresses are not the loads you would have had in statics, but the principle of equilibrium still applies. I mean, when you apply a load like this and you're trying to shear something off, do you see little bits of material fly out because they're not in equilibrium? No, of course not, right? They stay connected to the workpiece. So in order to stay connected, if there is some load, whether it's a stress type load or some other load, there has to be equilibrium somehow, and that's really where we're getting all these ideas. So one of the things we've assumed is that this stress is uniform over the area, but there's actually a couple things wrong with this. Now, we thought we could calculate the shear as force per area, being the shear area, and that's okay for first approximations, and it's alright for relatively thin materials, but there's actually two things wrong here. I'd like you to pause the video and think about it for just a minute and try to see if you can figure out what things would be wrong. Alright, so hopefully you've paused and you're back now and you've got some answers. I'll give you at least one thing that is wrong. That shearing cutter can't be right up against the fixed clamp, can it? In fact, even in the picture, there's a little bit of space. So in reality, when we're putting the shear cutter down and we're applying all this force, since there's a little bit of distance, wouldn't there be a moment here? And wouldn't that moment tend to cause a bending stress, or in other words, a normal stress that would come out and into this face that we're looking at, this shear plane? Absolutely, right? That's the case. That's what would happen here. So there's more than just shear. As a matter of fact, notice that so far all of these examples that we've studied so much are really kind of contrived, right? They're not what you'd see in the real world. In the real world, there's often both shear stress and normal stress, and we begin to see our theories break down here, right? Because calculating the stress, just F over A, well, there's other things happening to these little cubes, right? There's probably some normal stress going on here too. How does that affect the material? How does that cause failure? Obviously our goal in this case is to cause the workpiece to fail, but have you ever taken a piece of metal and tried to shear it? And have you ever had dull shears or shears that didn't work well, and instead of the material shearing, what happened was it bent over? Well, that's because a significant bending moment is being applied to the material and not enough shear stress is being applied, and so the material bends over in response to the normal stress rather than shearing in response to the shear stress. So both are present. In fact, that's very common. These examples, again, are extremely contrived. They're very rare examples that give you just one type of stress. The other thing that's wrong here, well, we learned that in reality, when you're shearing components, and when we're looking at shear stress, remember VQ over IT, in reality, the top and bottom of this workpiece will have no shear on it, right? There will be some shear distribution along the entire face. So really what we've done so far, it seems like is all garbage. It seems like we have to throw it all away. Well, the point of what we've done so far is not so much to give you tools for calculating stresses in real parts. That's not the point. The whole point of learning about shear stress and normal stress is so that you think about these things properly, that you understand what these things are, and you clearly differentiate shear stress from normal stress. Okay, these are two very different things. They are related to one another, but you need to have some intuition about how they arise, and bending stress is one very common way to generate normal stress, and shear, of course, can be generated in many different ways. In a beam, for example, there's an interplay between the two. The integral of the shear force, which causes shear stress, by the way, also causes a moment, which causes normal stress, right? So there's this relationship between all of them. And there's something else we've done that's kind of arbitrary here. But let's consider the last stress distribution that we've discovered so far. We discovered, that when we apply torque and loads to a rod, for example, the rod will deflect, and there will certainly be some shear or shear strain that's generated, and also shear stress. So you see the white element on the surface. Now this technically would be curved on the surface, but remember, these elements are infinitesimal things. We're imagining them getting smaller and smaller and smaller to where they basically have no size. So we can just imagine it as flat. And what we've done, it's kind of like a stamp. We've picked it up off of the surface of the rod and we're looking at it. And if we're torquing this thing, then we know there would be shear on the outer edges of this element. And if we were to extract it, we might realize that these stresses would have names. We could name them, couldn't we? I mean, after all, if we have an X and a Y direction axis, then we could call the shear on the right-hand face tau XY. Now, what is this? Well, you notice there's sort of a pattern here. There's tau XY on the left and right. There's tau YX on the upper and lower. What do these mean? Well, the way you read it is the shear stress tau on the X face. Notice we've got an X axis to the right, and that X axis is normal to the face, so it's a surface normal. So the surface on the right hand side of this cube is called an X face, as indicated by the X axis, which is normal to that face. So shear on the X axis in the Y direction. Notice that the shear is in the positive Y direction. Now notice that the shear on the left hand side of the cube is also called tau XY. And the reason is it's also on an X face. It's not a positive X face, it's a negative X face, and it's in the negative Y direction, but we don't care about that so much. What we care about is just naming these so that we know what face they're on and what direction they point. So tau YX then would be the shear on the Y face in the X direction. Now notice, for the sake of equilibrium, both tau XY and XY on the other side are the same. We may as well name them the same because they're going to be the same magnitude. And they cause a couple that has to be perfectly counteracted by tau YX, that other couple pair. And since the dimensions on each side of this cube are all equal, well then tau XY equals tau YX. And this is something you probably already know. I'm just reviewing with you now. Now, we realize that within the material, within the cross-section of the rod, the shear stress actually decreases. It's maximum at the outer face and goes to 0 at the center. And we can calculate that stress as TR over J, or if we're interested only in the maximum shear, that occurs at the outer surface and is TC over J, where R becomes the outer radius C. So it's maximum at the outer surface, and we can calculate it anywhere we want. Now, we also recently considered shear stress in beams, because if there's a shear load, there's going to be a shear stress. And if we were to look at just a beam that, say, is a simple rectangular cross-section and cut it at section 1, well, in reality, there is shear and there is moment there, right? We've got a line indicating, you know, the particular position along the length of the beam, and there's a shear V1 at that point, and a moment M1. Now, the moment's not at its maximum point, but it's still there. The shear is constant, but this is somewhat of a contrived situation, right? A simple loading, just a single point load in the exact center of the beam. So we've got a shear magnitude here and a moment, and both of those are going to give rise to shear stress and bending stress, or in other words, some normal stress. So if we extract this and look at it, you can see our isolated stress element. If we pull it down where we can look at it, again, remember, I'm not taking that black square off of the surface and looking at it normal to that cut surface. No, what I'm doing is the stress element, the right hand face is the cut face that you see above, okay? Whereas the left hand face is still in the beam material going to the left. So you notice we can calculate the magnitude of the shear stress. That's just VQ over IT. We just need V at location 1, so that's V1. And we need the moment in order to calculate the normal stress. Now notice that the moment's acting upward, so this would be a compressive stress acting into the face, right, into the cut face on the right hand side, and that the magnitude of that normal stress would be just negative M1 Y over I. Why M1? Well, because that's the section we're at. We're at section 1, right? The magnitude of the moment is just M1. So this is pretty simple, but wait a second. We haven't seen a cube like this yet, have we? We've never seen a cube that has both normal stress on it and shear stress. But if we were to try and understand what happens with the shear, it obviously varies along the entire section. It depends on how high that element that we've chosen is. In this case, it's at a height of y. And so calculating VQ over IT, Q would depend on the particular height, y. And we've studied all that. But of course, it's maximum in the center, minimum at the top and bottom. But so the stress element depends on where we take it as to what the magnitude of the shear stress would be, and it depends on where we take the element along the length of the beam as to what the magnitude of the moment would be. Of course, it depends on the height as well, right? Because at the neutral axis, I said moment, I meant normal stress. At the neutral axis, the moment causes no normal stress. So, it's highly dependent on exactly what point we look at in the beam, but it's pretty easy to come up with combinations of both shear and normal stress on our stress elements. This is the rule, right? Not the exception. The exception is a stress element that only has shear stress or normal stress. Alright, I already mentioned it's 0 at the upper and lower surface. Usually it's maximum at the neutral axis. That's not always the case, but usually that's the case. So here's our, I would say, complete stress element. Now we've already named tau xy and tau yx. Remember, it's the shear stress on the x face in the y direction. Doesn't matter if it's positive or negative y direction. And tau yx, the shear stress on the y face in the x direction. Again, positive, negative, doesn't matter. But if we name the normal stresses that we end up with, I would call them something like sigma x, indicating the normal stress on the x face. Remember that right face and left face are both x faces, so we'd have sigma x on either side. Now in this particular case, the way this is drawn is with x being positive, right, or sigma x both being positive. They could be negative. It just depends on the problem as to whether those are positive or negative. It's also possible, of course, to have normal stresses on the upper and lower surfaces, the y surfaces. In that case, these just arbitrarily are drawn compressive. They could be tensile as well. But notice that also these are normal stresses, and we could call them sigma y because they're normal stresses on the y face. Now remember, we're letting this cube shrink down farther and farther to where it's really just a point. So these stresses have to be applied at the center of all the faces. And then any other, any combination of load is really something that can be broken down, think of vector decomposition, into a normal and a shear stress. So it's possible we could, in reality, say on the x face on the right hand side, it's possible we could think of adding the shear stress and the normal stress and ending up with a vector that's sort of down and to the right. Wouldn't necessarily be at a 45-degree angle. We could go anywhere from, horizontal, where there's no shear, all the way down to no normal stress with just pure shear, right? So further, the shears don't necessarily have to point the way they are. Right now, the x faces are tending to cause clockwise rotation. That's why there's a CW past them, or just beside tau xy. And tau yx is tending to cause counterclockwise rotation of the cube. I think my directions are backwards because of the video, but you hopefully get the idea. So we name them clockwise or counterclockwise in addition based on how that pair on one face, on the x face or on the y face, tends to cause rotation. Now this is kind of interesting because if you think about it, all of these examples we have chosen a very arbitrary cut face. I mean, think about the workpiece that was clamped and we were shearing it. Well, okay, I mean it's a natural area to choose, right? Just that vertical area, but what's going on at an angle? Is that something we could consider? Is it something we should consider? Actually it is. If you imagine the cube, so look on the right hand side, that sort of orangish colored cube. We've got our cube sitting there with shear stresses and normal stresses on it, but this cube, the faces are cut matching however we arbitrarily decided to cut the part, whether it's a beam or a piston or whatever it happens to be. We've cut the thing in our minds in a very particular orientation, but that's arbitrary. The material doesn't care that we've imagined a cut face. What if we imagined a different cut face, a different angle for the cube essentially? We could still make up the part of an infinite number of these little cubes because they all shrink down to zero size, so that's no big deal. And if we do this, for this cube to be in equilibrium, the external loads are going to cause different stresses. I hope that makes some sense. One way to understand it is imagine, if you thought of just a cube. We'll look down at the little green cube in the middle that has forces on all faces. We can certainly imagine cutting that cube in half and looking at the stresses on that face, but we don't have to cut it that way. That's an arbitrary cut. What if we cut at an angle? What about if we cut at a 45-degree angle? What if, forget the 45 degree, what if we cut at, 45 and then turn it some also? Well, the forces have to somehow be balanced by the stresses on that face. And what I'm trying to get at here is that we could choose any cut direction we want. Now, there are actually three-dimensional cuts to consider, but for our sake right now, to keep things simple, we're only going to imagine, as in the upper figure, where we only rotate the cube about one axis, not two axes, because it becomes pretty complicated. Actually, it's not too bad. It's an extension of what we're going to do here. But it's, for now, for the sake of understanding, just imagine that we've got our stress element, but it's not necessarily here. It could be here, right? It could be at an angle. So look at the lower figure on the left-hand side, and you see our initial stress element with all of our shear and normal stresses, tau xy, tau x, sigma y, and sigma x. That's our initial stress element. But what if we were to rotate a little bit? What would the stresses look like? Could we find some interesting orientations? What do I mean by interesting orientations? Well, what I mean is orientations where maybe the shear goes to zero, or maybe the normal stress goes to zero, or maybe the shear stress is maximized. As a matter of fact, it is the case that you can find orientations where the shear stress goes to zero. You can also find other orientations where the shear stress would be maximized, because again, really, the material doesn't know about shear and normal stress. To it, it's just stress, and it's in a direction coming off the face that is not necessarily normal or just along the face itself, right? We choose a different orientation, and that's going to change the magnitude. All we're really doing is decomposing vectors here, right? There's a vector sum of tau xy and sigma x. And all we're really doing is saying, well, if we change the direction, we need a different magnitude of that vector, and oh, by the way, we have to redecompose it. So the point is that equilibrium still has to apply, and so I'll say without proof that what we're really doing here is something that we'll call Mohr's circle. Now, it's not Mohs circle like the Three Stooges, it's Mohr, M-O-H-R. Like the word, I want more pie, okay? Mohr's circle. And all we're really doing, if you think about it, is saying, as we rotate this cube in our mind, the magnitude of the normal stress and the shear stress are going to kind of trade off between each other. And it turns out that they trade off essentially on the surface of a circle. So if you were to take the initial stress element in the lower left-hand corner and plot it on a shear stress, vertical axis, and normal stress, horizontal axis, you could plot, say, the right-hand face. Okay, so the right-hand face, it's the same as the left-hand face. Okay, they're the same, right? The magnitudes are the same. There's nothing unique about either one. Let's choose the right-hand face to plot, and there our sigma x is a positive thing. So on the sigma horizontal axis, we need to move over to sigma x. So hopefully you see that vertical line there where sigma x is located. Going up from that line, what we would do is plot a point labeled point 1 that indicates the magnitude of sigma x, but also the magnitude of the shear on that same face, on that right-hand x face. Now that shear is tau xy. And so the magnitude of point 1 on the y-axis is equal to tau xy. So if we were to label this on the vertical axis, the shear axis, we'd label it tau xy. And you notice the height b is tau xy. Obviously we're going to build a triangle here where the height b is just tau xy, but we'll get to that a little bit later. The point right now is that point 1 is just an xy pair that you've probably been plotting since maybe middle school or high school. It's just that our axes aren't called x and y anymore. They're called normal stress and shear stress. Now notice that tau xy on the x face points downward. It tends to cause a clockwise rotation of the cube. By convention, we're going to make the shear axis clockwise in the upward direction and counterclockwise in the negative direction. So if our shear tends to cause a clockwise rotation, we'll just put it on the positive side of the vertical axis, okay, or the upper side. Okay, so we've got this point plotted, sigma x, tau xy. Okay, we could also plot the y face. Now to plot the y face, let's look at it. It's sigma y. Now, as I said before, it's not always true that this normal stress will be negative, but in this particular case it is. And you notice that tall yx tends to cause counterclockwise rotation of the cube. And so to plot that point as point 2, you notice that we're to the left side, we're to the negative side of the normal stress axis, so on the negative sigma side. You can see sigma y there. And since tau xy tends to cause counterclockwise rotation, we got to put it below the x-axis now, or below the sigma axis, I should say, the horizontal axis. Now, these 2 points define a circle that is centered at O. One interesting thing about Mohr's circle, at least for 2 dimensions, even for 3 dimensions, it's always centered on the horizontal axis. We're never going to draw a circle that has its center with any positive or negative shear, okay? So it'll always be centered on the x, or constrained on the x-axis. So if that's the case, then only 2 points would define an entire circle. And as we rotate the stress element, basically all we're really doing is rotating the points on the circle. Now, one thing you have to be careful about, you notice that from the initial stress element on the lower left-hand corner to the principal stress element, there's a rotation that has occurred that is a clockwise rotation in magnitude of phi. So on Mohr's circle, the equivalent of that is actually a rotation of 2 times phi. The reason for that, if you think about it, kind of makes some sense, because notice the x face is 90 degrees from the y face, right? All I got to do to move the cube, that was the x face to the y is rotate the cube by 90 degrees. But on Mohr's circle, the y face is plotted 180 degrees away from point 1, right? And so basically what that means is a rotation of 1 degree on the cube is 2 degrees on Mohr's circle. So if we rotate by, positive, well, I guess negative, depends on whether you consider clockwise or counterclockwise positive, but if you rotate clockwise by an angle of phi, then you have to rotate from point 1, point 2, an angle of 2 phi, and what we're doing is rotating to the point where we end up with our 2 points on the normal stress axis at sigma 1 and sigma 2. These are very important points. They're called principal stresses. These are the points where there is no shear, and that should make some sense from Mohr's circle, because look, sigma 1 and sigma 2 are on the sigma axis. They have no height, right? There is no shear at that point. So what we've done is rotated the cube to a point where we found an orientation where there is no shear stress on this cube, whether it's on what was the original x face or the original y face. They're now both shear equal to 0. Now, on the other hand, we could rotate these the other way. So let's go back to point 1, point 2 in that inclined line. And what if we rotate a distance in the counterclockwise direction of phi prime, just as in the maximum shear stress element on the right? So going up to Mohr's circle, what we'd be doing is rotating point 1 and point 2 in Mohr's circle by a rotation of 2 phi prime. Okay, again, twice the angle of rotation, so that we end up at the top and bottom of the circle with what would be the maximum shear stress. Now hopefully this makes some sense, right? Because those are the points on the circle that have the largest value of tau. They're farthest on the tau axis, whether it's positive, clockwise tau, or negative shear stress. So this orientation is actually really important. Both of these are important because generally some materials, brittle materials, fail due to normal stresses, whereas ductile materials fail due to shear. So if you're asking the question, number one, how much load is, or how much stress is there to cause failure in this material, you need to know what the maximum is, and you need to know what you want to look at. Do you care about normal stresses, or do you care about shear stresses? If it's a brittle material, then you better find the principal stresses, because those are the ones that are going to cause failure. If it's a ductile material, you better find tau max, because those are the stresses that are going to cause failure. You guys have probably pulled dog bones apart before, dog bone samples in the tensile test machines. When you did that, did you notice that there was always an angle of the face? It may have been an angle that you could see from the front, or maybe it was an angle, forward back along the thickness of the material, but there was always an angle. The reason for that is you're probably pulling apart either steel or aluminum dog bones, both of which are typically ductile materials, unless of course they've been heat treated and quenched and so forth. But in that case they would be brittle and they would just break horizontally. But most of the time we give you guys ductile materials to pull apart, and so you see necking down, and you see a failure plane that is not just straight through the dog bone, normal to the axis of the dog bone. Rather, what you see is an angled plane. And the reason for that is because from Mohr's circle, that horizontal plane from the dog bone, cutting the dog bone that way, is arbitrary, right? Rather, cut it at an angle where, find the angle where you see the largest shear stress. That's the plane along which failure is going to occur, because the shear stress is going to be too large for the material to take, and the largest direction of that shear stress is along that inclined plane, and so that's the way it's going to fail. So this is actually a very useful technique. It's very important, and really probably the most important thing to understand from this is that really normal stress and shear stress can be combined to generate either more shear or more normal stress, and you need to be aware of that. You can't just do all your calculations based on some arbitrary plane that you choose. The material may not choose to fail along that plane. It doesn't care what you think, right? It's going to fail along the plane where the maximum stress occurs that it's sensitive to. That's simply how it works. So Mohr's circle is simply a tool to allow you to transform normal stress and shear stress into one another, and to locate the angles where these failure planes would occur. So Mohr's circle is a very important geometric thing, and we need to study it. Notice there's a triangle that sort of appears here. Let's look at some of this geometry. For one thing, the triangle goes from O to point 1 down to the axis. That's the triangle I want to look at. And notice the height of it, B, is tau xy. It's the initial stress elements, the stress on the x face in the y direction, that is shear stress. So that's the height of this triangle. The base length of it is actually what we'll call A. It's 1/2 of sigma x plus sigma y. Now what does that mean? Well, sigma x, you notice where that's at on the normal stress axis on the right hand side. Sigma y is over on the left hand side, and there's a plus sign here. I think that I scanned this and I forgot to fix it. It should be, it's a little bit confusing. When we're trying to get just the distance, notice sigma y is a negative thing, and so really I should say minus sigma y, but I've got it as plus because conceptually I just want the magnitude of sigma x and sigma y. Well, let's see. Let's make up some numbers and see what would happen. So if sigma x looks like it's to the right a little bit more, so I'll count just what they've got on the tick marks. 1, 2, 3, 4. So sigma x is 4, whereas sigma y is -3. Okay. So if I take 4, let's see, 1, 2, 3, 4. Yeah, I got that right. 4 plus 3. Well, that's 7, right? So 7 divided by 2 would be 3.5. So yeah, that makes sense. So A would be the sum of the absolute values divided by 2. But to find O, that's something a little bit different. That's the average normal stress. And that average normal stress occurs at, it's less than half of a tick, right? It's less than half of one of those marks. So let's see if we can come up with that. The way you do it is you simply add not the absolute values of sigma x and sigma y, but their actual values. So we said sigma x is 4, sigma y is -3. The sum of those is simply 1. 1 cut in half would be the average normal stress. So the location of the center of our circle marked sigma average. And then the hypotenuse is just the square root of the sum of the squares, right? So it's just square root of a squared plus b squared. And that length, that hypotenuse, is really important because if you think about it, as you rotate your stress element using Mohr's circle, point 1 is going to move up to the point right above O, the center of the circle. And in that case, the radius is still the same. As a matter of fact, that radius r is equal to the maximum shear stress, which is really important because most of the time that's what we care about, since most of the time our machines use ductile materials and are designed from those materials, and we want to know when they'll fail and at what angle and so forth. So that radius, or that hypotenuse distance, is a very important thing that we'd like the ability to calculate. The principal stresses are also very important because if you're dealing with a brittle material, you need to know the maximum magnitude of normal stress and the angle at which it occurs. In summary, here are some of the equations that you would need to use. To get sigma average, we have to add sigma x and sigma y, whatever they be, whether they're positive or negative, it doesn't make any difference. Leave them as they are, add them, and then take half. So be careful, because sigma average and the bottom length of that triangle are not the same thing. The whole point of this equation is to find the center of Mohr's circle. That's really what it's good for. Now, the maximum shear stress, you'll notice that this is actually the dimension a squared, that's the first term, plus b squared. That's really what it is. And notice that these stresses, tau xy, sigma x, and sigma y, come from the initial simple element that's relatively easy to analyze, right? We took an arbitrary cut because that cut made it easy for us to calculate the magnitude of all the shear and normal stresses. Well, the nice thing about it is once we get those, we can plug them into this equation and calculate the maximum shear stress. Now, interestingly enough, as I said, this is just the R, the capital R. It's the radius of the circle. And so A is the length of that triangle's base, and B is the height, which is just tau xy. So you see the negative sign here that should be on that Mohr's circle slide that I worked with a moment ago. The principal stresses can be located based on the average stress plus or minus the maximum. Now remember, tau max is really just the radius of Mohr's circle. So all we're really doing here is saying, okay, if you know where the center of the circle is and you go out a distance r on the sigma axis, well, that's one of the principal stresses. If you subtract tau max, which is the radius, then you're moving back, towards the negative side, not necessarily on the negative side of the normal axis, but moving towards the negative side of the normal axis, and that's the lower principal stress. Now we have to be careful because we always assign the number sigma 1 to the maximum normal stress, whereas sigma 2 is always assigned to the minimum normal stress, and that's something you need to remember.